So you see, this is what I told you, that this is the BCC structure. But this time, this is chlorine and that is chlorine, and the center is cesium. The rest is the same. Remember, if one side is A, then this bottom diagonal was root 2A and this diagonal was root 3A. So this is there. But this root 3A is not R plus 2R plus R. That was 4R earlier. It is 2R of this time and 2R of this kind. So this is the only thing, that root 3A is equal to 2R of chlorine and 2R of cesium, right? And the atomic packing factor is again volume of atoms in the unit cell upon the volume of the unit cell. So with this, we proceed further. We know that root 3A is 2 small r plus 2 capital R. So for 1 R, put, right, the value of cesium and chlorine that was given 0.17, and for the other 0.181. So root 3A is equal to this. So A is equal to this much. You find this A. And what is the volume of the cube? A cubed. So cube of this will be the volume of the cube. So ionic packing factor is the volume of the atoms upon the volume of the cube. Now, how many atoms of cesium? 1 atom. How many atoms or ions of chlorine? 1. And what is 1 sphere? 4 by 3 pi r cube. So 4 by 3 pi r cube for cesium, 4 by 3 pi r cube for chlorine. And this A is this number. So, right, 4 by 3 pi r cube. And this R is 0.17 cube. This R is 0.18 cube. And the total answer is 0.68. So 0.68 is the ionic packing factor for cesium chloride. Now this is, of course, this number will not be exactly this. They have rounded it off. So please try to find out whether it is 0.679 or it is 0.681, right? Write at least 3 decimal places, where the third decimal place you round off, as I always want to say. But this is brilliant, that you see, we know from chapter 3 that if it is a BCC material, then the atomic packing factor was 0.68 roughly. Now it is a ceramic material. Cesium chloride is a ceramic material where it is a compound, ionic compound of cesium and chlorine. But even now, if it is a BCC structure, then the ionic packing factor is almost the same 0.68 as it was for pure metals. So this is a brilliant thing, but now you know how to do this calculation, right? So now you can. So the second category or class is sodium chloride. Before we go into that, again, just try to wonder, right? Wonder. You see, what is sodium chloride? Sodium chloride is common salt. But did you know until now ever that the common salt is a ceramic? Every day of your life, you eat a ceramic, and the ceramic is very good for your health and so on, right? So this is remarkable, but it is there. So now this is the sodium chloride crystal structure. It is an FCC type. If you see only these light ones, then they are like FCC, right? On the corners and on the center of the face. On the corners and on the center of the face. So any one of them, like sodium or chlorine, forms a standard FCC. So all sodium or all chlorine is all on all of the 8 corners and half atoms on all of the 6 faces. Then whatever interstitial sites are remaining, they are filled by the other one. So you see, this is one corner, this is one corner, this is the interstitial site between them, this is filled by the other one. This is one corner, that is the other corner, in between there is the other one. So all of the standard FCC sites are filled by one of the materials, for example sodium, and all of the interstitial sites are filled by the other, like chloride. So if you see the box type, then here is the main one, and on the face centers, and then in between the other one is there, and all of them are touching each other of you. So here the light one is chlorine, the dark one is sodium. So here we are showing that the corner ones are sodiums and the middle ones are the chlorines. But we could interchange them, because you see this is one, but just beside the other, this one, for example, this chlorine will be surrounded by sodiums in the same way. And because of this structure, this has a tetrahedral type of a structure like this. If you see 1, 2, 3, 4, they are joined. Then the other one is here, the other one is here, and the center there is one here. And all of them are touching each other, So if you see this dark one is touched by these 4 and these 2 6. So the coordination number is 6, right? So sodium chloride crystal structure of this particular ceramic is this tetrahedral type of a structure, which is basically FCC, where the interstitial sites are filled up by the other, and its coordination number is 6. Now, of course, if it is sodium and chlorine, then the radius ratio, we just divide the values and you get a radius ratio of 0.56, which, if you go back to the table, will be the same as the value for the coordination number of 6. Magnesium oxide, calcium oxide, nickel oxide, iron oxide, all of them also have the same crystal structure as sodium chloride. So we are studying sodium chloride here, but if we are given any problem about calcium oxide or iron oxide also, we will solve it in exactly the same way as we are doing this one, right? So this is the second class. The first class was cesium chloride and many ceramics which behave like that. The second class is now sodium chloride and many other ceramics which behave like this. So let's straight away, because you now have the background of ceramics and so on, calculate the density here, density of sodium chloride, And what is given inside? The ionic radius. The ionic radius for sodium is this, and for chlorine is this. And the atomic mass of sodium is this, and chlorine is this. Of course, this atomic mass you can get from the atomic table and so on for sodium and chlorine. And these radii will be almost the same as this is the ionic radii, right? Ionic, sodium plus, but they will be almost the same as sodium and chlorine. So if you have an atomic table where the values of sodium and chlorine are there, the radius of both of them and the mass of both of them, then we can solve this problem. Now, right, as I always say, you just write down density unknown, ceramic sodium chloride, radius of sodium given, radius of chlorine given, atomic mass of sodium given, atomic mass of chlorine given, and the only thing is density. So now don't go further. You should stop here in my video lecture, and as I always recommend, you take a piece of paper, you write the knowns and unknowns, and then you try to start to solve it yourself. So how will you start? What is density? The basic definition of density everybody knows is mass upon volume. So that definition is there. But on a crystal level, this is what mass and what volume? The mass of the atoms in a unit cell, right? The mass is the mass of the atoms in a unit cell. And what is the volume? The volume of the unit cell, which is always A cubed if it is BCC or FCC. And this is an FCC, right? So the mass of the atoms in this unit cell and the volume of the atoms. Now you should draw very quickly the same diagram. You have an FCC in which the intermediate sites, FCC means all, if you take any one face, on FCC if you take any one face, all 4 corner atoms are there. For example, they are chlorine, and there is one central atom which is chlorine. So this is chlorine. Now on each line of the face, between the 2 chlorines, there is a sodium. So there are 4 sodiums in between, right? So that is the diagram you draw. Now you want to find 2 things. The A here is equal to what, right? You have 1 chlorine, then 1 sodium, then 1 chlorine. This is on one line of the face, isn't it? On any one line of the face. This one line of the face is A, and you will see now that this is equal to 2 capital R, 2 small r, right? Because half atom of chlorine is there, 1 atom of sodium is there. So half atom means 2 times R, and 1 atom means 2 times R. So A is equal to 2 small r plus 2 capital R, or 2 R of sodium plus 2 R of chlorine, right? Okay. Now, how many equivalent atoms are there in FCC? If you go back to your chapter 3, then in FCC, there are 8 corner atoms. So 8 into 1 by 8 is equal to 1 full atom. And there are 6 atoms which are on the faces, and each one of them is half. So 6 into half is 3 atoms. Therefore, 1 plus 4, total of 4 atoms in a FCC unit cell, right? So here on the standard FCC sites, there is, say, chlorine. So there are 4 chlorine atoms. 4 chlorine atoms. Now, rather than counting geometrically how many sodium are there, you know that the chemical formula is sodium chloride, NaCl, +1 -1. So whatever chlorine is there, it is exactly balanced by sodium, isn't it? +1 -1. So if there are 4 chlorine, there have to be 4 sodium. If they are not there, then the atomic charge will be unbalanced, and this will be an electrified ion, right? So it will not be a ceramic which is balanced. So therefore, in a normal FCC, there are 4 equivalent atoms. Therefore, in sodium chloride, there are 4 chloride ions. And because there are 4 chloride, therefore, by balance of electronegativity and so on, or valence, there are also 4 sodium atoms. So now you have it. Of course, you have to know the Avogadro's number, because atomic mass is given in gram per mole. So you divide it by Avogadro's number, which is the number of atoms per mole. Therefore, then you find the mass for one atom and multiply it by 4. And you find the value of A is equal to 2R plus R, and A cubed is equal to volume. So this is how you will do it. So let me show you. So right, I told you that draw any one face. So if this is any one face of a face centered, then this corner, this corner, this corner, this corner is the same atom, and in the center it is the same atom. Normally they will touch each other. Normally this will touch each, but because this is an interstitial solution, so between this and this, there is the other one. If this is chlorine, this is sodium, right? So because this is sodium, so they are pushed back a little. So now this does not touch this, but this touches this and this touches this. So this, in this way, they are all touching. They are all touching each other, isn't it? But this central one cannot touch. But this is how it is, that these dark ones are the chlorine and these light ones are the sodiums. And if you see any one side, this is A, this is A. So this is capital R plus 2 small r plus capital R. So 2 of capital R plus 2 of small r. So A is equal to 2R plus 2R, and then A cubed will be the volume. And this 1R is for sodium, 1R is for chlorine. So you find A from here, put R of sodium, R of chlorine here, find the value of A, cube it, and A cubed will be the volume. And as I just told you, the equivalent number of atoms will be 4 sodium and 4 chlorine. So let us go ahead and see. Right, so yes, whatever we have just told you is there. And if you want to find the mass, then 4 sodium into the mass of sodium, 4 chlorine into the mass of chlorine upon Avogadro's number. So this is the total mass in this unit cell, right? This is the total mass of atoms, chlorine plus sodium. So this is the total mass, and A is equal to 2R of sodium, right? Plus 2R, right? So this is R sodium, R chlorine, you radius of sodium, radius of chlorine. So A is this value. And they are directly converting to centimeter here, so that you can directly find gram per centimeter cube as a standard unit. And volume is A cubed. You could have done nanometer cubed directly and then convert, or you can convert nanometer to centimeter and directly find centimeter cube. So now you have so many grams mass and so many centimeter cube. So the unit is gram per centimeter cube, which is the standard unit of volume. So it is, right, the density of sodium chloride, common salt, is 2.14 gram per cubic centimeter. Of course, you could convert the grams into kilograms, and you could convert nanometer into meter, because the other standard unit of density is kilogram per meter cube. So do not give us an answer in gram per nanometer cube. The value is correct, but you cannot find this density value in any tables. So always try to do either gram per cubic centimeter or kilogram per meter cube. So we will take a small break and we will come back to you. We'll stop here today and see you next time, inshallah. Ma'as salama.